Welcome to my channel Speak with Math. In this video I am discussing about integration of functions of two variables, that is double integration. Let f of xy be a continuous function of two variables x and y defined on a region R bounded by a closed curve C, and the region R be divided in n subregions of areas delta A1, delta A2, etc., delta AN. And let xi and yi be any points in the subregion of area delta ai, and consider the sum Sn is equal to summation I is equal to 1 to n f of xi yi into delta ai. Let f of xy be a continuous function of two variables x and y defined on a region R bounded by a closed curve C. The region R be divided into n subregions of areas delta A1, delta A2, etc., delta AN, and xi and yi be any points in the subregion of area delta ai, and then the sum, we can consider the sum Sn is equal to summation I is equal to 1 to n f of xi yi into delta ai, and the limit of this sum is defined as the double integral of f of xy over the region R. We can mathematically write it as double integral over the region R f of xy dA is equal to limit n tends to infinity summation I is equal to 1 to n f of xi yi into delta ai. The region R is called the region of integration. In order to simplify the evaluation of the double integral, we can consider subregion Ri of R, and one common choice is the rectangular subregions or rectangular grids obtained by subdividing R by lines parallel to the coordinate axis, that is parallel to x and y axis. Then the area of a typical rectangular grid is delta ai is equal to delta xi into delta yi. Then the above integral becomes double integral over the region R f of x y dA is dx dy is equal to limit n tends to infinity summation I is equal to 1 to n f of xi comma yi into delta xi delta yi. Now consider the first problem. Evaluate double integral 0 to 1 to 2 x square plus y square dx dy. First integrate the inner integral. So integral 0 to 1 integral x square plus y square dx. That is integral x square dx is x cube by 3 plus y square into integral dx is x. Limits varying from 1 to 2 dy is equal to integral 0 to 1. If we apply the upper limit, 2 cube is 8. 8 by 3 plus y square into 2 minus 1 by 3 minus y square dy. Now this becomes integral 0 to 1. 8 by 3 minus 1 by 3 is 7 by 3 plus y square into dy. Here integral 7 by 3 dy is 7 by 3 y plus y square dy. Integral y square dy is y cube by 3. Limits varying from 0 to 1 is equal to 7 by 3 plus 1 by 3 minus 0 is equal to 8 by 3. So the answer is 8 by 3. Now consider the second problem. Evaluate double integral xy dx dy over the first quadrant of the circle. X square plus y square is equal to a square, and this is the equation of a circle passing through origin and radius a. The first quadrant we have the portion of circle like this. The radius is a, so this value is a. Here to here this a, here also a, and the circle meets the y-axis when x is equal to 0, and this implies y is equal to plus a in the first quadrant. Hence in the first quadrant, consider strips parallel to the x-axis. I am drawing one such strip. Consider strips parallel to x-axis, and each strip varies from x is equal to 0. Here the value of x is 0 to x is equal to root of a square minus y square. From this equation, x square is a square minus y square, or x is equal to square root of a square minus y square. So each strip varies from x is equal to 0 to x is equal to root of a square minus y square. To cover the entire region, each strip moves from y is equal to 0 to y is equal to a. So the limits of integration for x is equal to 0 to x is equal to root of a square minus y square, and for y is equal to 0 to y is equal to a. Here if we are considering a strip parallel to the x-axis, x value varies from x is equal to 0 to x is equal to root of a square minus y square. To cover the entire region, we have to consider more strips parallel to x-axis like this. So y value varies from y is equal to 0 to a. So the limits of integration for x is equal to 0 to x is equal to root of a square minus y square, and for y is equal to 0 to y is equal to a. Hence the region enclosed in the first quadrant of the circle is given by the set of inequalities 0 less than or is equal to y less than or equal to a, and for x 0 less than or equal to x less than or equal to root of a square minus y square. Then the integral, double integral is y equal to 0 to a, x equal to 0 to root of a square minus y square xy dx dy is equal to integral 0 to a. First integrate the inner integral. So xy dx is integral xy dx is what? X square by 2 y, limits varying from 0 to root of a square minus y square into dy, and is equal to integral 0 to a 1 by 2 into y into x square is, here the value of x for the up, if we are applying the upper limit, that is a root of a square minus y square. Here we have x square, so a square minus y square into dy. If we apply the lower limit, it becomes 0. So 1 by 2 into integral 0 to a square y minus y cube into dy. So I is equal to 1 by 2 into integral a square y dy is a square y square by 2 minus y cube dy. Integral y cube dy is y raised to 4 by 4. Limits from 0 to a is equal to 1 by 2 into a square by 2 into a square minus a raised to 4 by 4 minus 0 is equal to 1 by 2 into a raised to 4 by 2 minus a raised to 4 by 4 is equal to 1 by 2 into a raised to 4 by 4 is equal to a raised to 4 by 8. So the answer is a raised to 4 by 8. Now consider the third problem. Evaluate double integral x square plus y square dx dy over the region S in which x greater than or equal to 0, y greater than or equal to 0 and x plus y less than or equal to 1. In this case, first draw the line x plus y is equal to 1. X plus y is equal to 1, and in x-axis y is 0 and in y-axis x is equal to 0, and x plus y is equal to 1 is a straight line. Now consider a strip parallel to the x-axis and then the points on the strip varies from the line x is equal to 0 to x is equal to 1 minus y. Here x plus y is equal to 1, then the value of x is 1 minus y. So for this strip x varies from x is equal to 0 to x is equal to 1 minus y. So the points on the strip varies from x is equal to 0 to x is equal to 1 minus y. So the limit of x are x equal to 0 and x is equal to 1 minus y. To cover the entire region, such strips should start from the minimum value of y, that is y is equal to 0 to the maximum value of y. Here the maximum value of y is what? Y equal to 1 to the maximum value of y. Here the y value is 1. To cover the entire region, such strips should vary from y is equal to the minimum value of y to the maximum value of y, that is y is equal to 0 to y is equal to 1. Hence the limits of y are y is equal to 0 to y is equal to 1. So the region of integration is We can use the set of inequalities to represent the region of integration 0 less than or equal to y less than or equal to 1 and 0 less than or equal to x less than or equal to 1 minus y. So the given integral is double integral y equal to 0 to 1, x is equal to 0 to 1 minus y, x square plus y square dx dy, 0 to 1. Here integral x square dx is x cube by 3 plus y square x into dy is equal to integral 0 to 1. If we apply the upper limit, 1 minus y the whole cube by 3 plus y square into 1 minus y. If we apply the lower limit, it becomes 0 into dy. I am taking 1 by 3 outside of integration. So integral 0 to 1, 1 minus y the whole cube plus 3 y square into 1 minus y. I am taking 1 by 3 outside. So here we have 3 into y square into 1 minus y dy. Now, so we get 1 by 3 into integral 0 to 1 minus y the whole cube, that is a minus b the whole cube form. So a minus b the whole cube is a cube minus b cube minus 3a square b plus 3ab square. So here a is 1. So 1 cube is 1 minus b cube, that is y cube minus 3a square b, that is minus 3y plus 3ab square. So plus 3y square. Here 3y square into 1. So plus 3y square plus 3y square into minus y. So minus 3y cube into dy. So this is equal to 1 by 3 into integral 0 to 1 minus 1 minus y cube minus 3y cube. So 1 minus 4y cube plus 3y square plus 3y square. So 6y square minus 3y into dy. So 1 minus 4y cube minus 3y plus 6y square into dy minus 3y into dy. This is equal to 1 by 3 into integral 1 dy is y minus 4 into y cube dy. Integral y cube dy is y raised to 4 by 4 plus 6 into here y square dy. So y cube by 3 minus 3 y square by 2. Limits varying from 0 to 1. So this is equal to 1 by 3 into y minus y raised to 4 plus 2y cube minus 3 by 2 y square, limits varying from 0 to 1. 1 by 3 into y minus y raised to 4 plus 2y cube minus 3 by 2 y square. We apply the upper limit, this becomes 1 by 3 into 1 minus 1 raised to 4, that is 1 minus 1 plus 2 minus 3 by 2. If we apply the lower limit, it becomes 0. So 1 minus 1 is 0. 1 by 3 into 2 minus 3 by 2 is equal to 1 by 3 into 4 minus 3 by 2 is equal to 1 by 6. So the answer is 1 by 6. Thank you.